In the previous topic, we saw how we could use a single mirror or a single lens to form an image, sometimes real, sometimes virtual. But we have many more possibilities if we combine a whole series of optical elements like mirrors and lenses. Examples you might be familiar with are things like high-quality camera lenses or projection systems. One of the things we often want an optical system to do for us is to magnify things, thinking of telescopes or microscopes. In fact, the idea of magnifying can be done quite simply. We've already seen an example that's quite straightforward to do. Let's go back and look at our single lens, and now let's place our object inside the focal length. We'll do the same rules as we did before. Let's take a ray that's parallel to the axis. It will go through the focal point on the other side, and our other ray that we'll consider goes through the centre of the lens, and it's undeflected. It goes straight through. Now, of course, these rays, as you can see, are diverging again. So we trace them back to see where they appear to come from, and we'll have our image formed where they overlap. Once again, we have a virtual image. It's right way up, and it's magnified. And this is exactly what you do when you use a magnifying glass. You take a converging lens like we have here, and you put it up nice and close so that the object you want to look a magnified version of is inside the focal length. Of course, if you use a magnifying glass to try to magnify a distant object, it doesn't work very well at all. We've seen in the previous topic what happens when the object is outside the focal length. So a magnifying glass already does part of the job for us, but it's limited to objects that are close enough for us to put inside a focal length. That's not so useful if we want to look at some distant object. Have a nice up-close look at the moon, for example. It's pretty hard to get the moon inside the focal length. So we can do a bit better by building a simple telescope. And we'll see here with a simple telescope, we now have two lenses. Now the first lens that you see there on the left, we call the objective lens. It's closest to the object that we're trying to look at. Now I haven't drawn the object here because the object might be so distant that in fact we can't fit it onto the screen. But we've seen some light coming from that distant object arriving at the objective lens. The light's almost parallel. Maybe we're looking at a distant star, perhaps. And if we do our ray tracing through our lens, we find that that light will in fact form a small real image not too far from the focal length of that first lens. We've called it f1 here in the diagram. Now that's not very useful. We wanted a magnified version of that. But in fact we can make that first image fall within the focal length of our second lens in our telescope. The second lens here is called the eyepiece lens because it's closest to your eye when you're looking down the telescope. So the eyepiece lens here typically has a fairly short focal length. The image that we had from the first lens, the objective, now falls inside the focal point of that eyepiece lens. And as we saw on the previous diagram, if we've got an object inside the focal length, we'll get a magnified, right way up, virtual image. Now, this image you see here is already upside down, so the eyepiece takes the upside down lens and gives us a right way up version of an upside down lens. If you didn't follow that, the bottom line is our telescope actually inverts the image. We don't mind if we're looking at a distant object in the sky. We don't care if that particular star or planet is upside down. But if you're using a telescope on the Earth and you want to see something in the distance, it's a bit disconcerting if it's upside down. We have to do a little bit more optics to actually make sure our land-based telescope gives us things the right way up. Another point to note here is the main job of the objective lens is to collect as much light as possible. So typically we'd like to have our objective lens really quite large. In fact, sometimes so large in a telescope that it's difficult to make a nice, perfect glass lens. What's often much easier to make is a very large diameter mirror. And we can construct a telescope very similar to this, where the objective is not a focusing lens, but a focusing mirror, like the concave mirrors that we saw earlier. Another example you might like to use that's very, very similar to our telescope here is a microscope. But here we have the advantage that we can use the things that we're trying to look at to be close to our objective lens. So our objective lens doesn't need to be a large light collecting lens. It can actually be a magnifying lens itself, and our microscope is usually doing the job of two magnifications with the two lenses that are involved. Now what we're going to move on to next is another example of refraction, but in fact where refraction is going to lead us to a type of reflection called total internal reflection, and it's amazing how much of our modern world is going to rely upon that fact.